All right, this slideshow is going to have in it a number of You Try It problems. If you find them hard, just realize that when you try hard problems, you learn more from them. So don't get discouraged. Just try to learn as much as you can. Okay, which of the following bases is strong enough to completely deprotonate propyne? Well, if I look at these, ammonia is a very weak base. Now the conjugate base of ammonia is strong enough, but not ammonia. It's too weak a base. Ethanol is not a base, and so it's not going to deprotonate propyne at all. Sodium hydroxide is not a strong enough base to deprotonate propyne. The only one that is a strong enough base is the sodium amide. Which alkyl halide will react fastest with the acetylide anion in an SN2 reaction? Well, if I go through, you have to remember the things that you learned from last semester. And an SN2 reaction, what's fastest? Primary, unhindered substrates. What's slowest? Tertiary, hindered substrates. So we're going to look at these and we're going to try and figure out which one is least hindered. Of course, primary is least hindered. B is secondary, so that's more hindered. So primary will be faster than secondary. And then this is tertiary, so that's slowest of all of them. But look at this. This is a primary, 1-bromo-2-methylbutane. But notice the 2-methyl. That's going to give a little bit of steric hindrance, so that will be slower than the 1-bromopropane. So which one is fastest? 1-bromopropane. In addition to sodium amide, what other base can be used to convert 1,1-dichlorobutane into 1-butyne? Well, if I look at this, we really haven't used anything but sodium amide in any of our deprotonation reactions. So now you have to use your head and think a little bit. If I look at these, they all have about the same strength because they're all alkoxide. So it's not that one is a stronger base than the other. Since all we're doing is trying to deprotonate the 1-butyne so it can do an SN2 reaction, what else could these do if they're all going to be strong enough to deprotonate the 1-butyne? Well, if I look at these, all of these are primary alkoxides and have no hindrance. This is very sterically hindered. All of these can do SN2, which you wouldn't want to have happen because all you want this to do is do a deprotonation reaction. So the T-butoxide here would be the best one to use. Select which is the most effective way to synthesize cis-2-pentene from 1-propyne. Well, the first thing you're going to notice is 1-propyne to 2-pentene, you're adding 2 carbons. So you know you're going to have to make an anion and then do an SN2. And if I look at this, all of these have as an option sodium amide to deprotonate the propyne. How many carbons do you need to add? Well, you need to add 2. So that's going to eliminate B. It's got to be either A, C, or D. Now, on all of those, you have a 2-carbon substrate, and either bromine or iodine are fine. So really what we have to look at is reduction. It says cis-2-pentene. If I look at A, I can see the reducing agent will take it down to the alkane, and so that would be pentane it would take it to. So we eliminate that possibility. If I look at the sodium and ammonia, that reducing agent gives you a trans-pentene. So we eliminate that one. The only one that would give you a cis-ene would be the Lindlar catalyst. So C would be the correct answer. What is the structure of compound Y in the following synthetic sequence? Okay, if I look at this synthetic sequence, we can see that we're taking a terminal alkyne and treating it, that should be a 2 here, not a 3, with sodium amide. Sodium amide will deprotonate it so that you can do an SN2 on this primary alkyl bromide. That's going to end up giving us 2-pentyne. So compound X is going to be 2-pentyne. If I use hydrogen and the Lindlar catalyst, that's going to give me the cis-alkene. So compound Y will have to be 2-pentene that is cis. And that's the answer that is shown. Which reagent would accomplish the transformation of 3-hexene into trans 3-hexene? Well, if I look at all of these reducing agents, this would give a cis-alkane. Well, this would give an alkane. This would give a cis-alkene. This would give a trans-alkene. And this would not reduce. So this is just a base in ammonia would be the solvent. So the only one that's going to give me a trans-alkene would be C, sodium and ammonia. What product is formed when 2-butyne is treated with ozone? Well, 2-butyne is going to give you a 2-carbon acid. So if I look, this ozonolysis does not give a ketone. It gives a carboxylic acid when it's an alkyne. It does not give an aldehyde. And it does not give an alcohol. What does it give? It gives a carboxylic acid. So 2 of the carbons on the left would be converted to acetic acid, and 2 carbons on the right would be converted to acetic acid. Okay, put these compounds in order of increasing carbon-carbon bond length. Notice we're looking at bond length. What is the correlation? The correlation is as the number of bonds increase, your bond length decreases and your bond strength increases. So ethane will have the longest bond, ethyne will have the shortest bond. So if we're going to put it in increasing bond length, it will have to go ethyne to ethene to ethane. So C is the correct answer. How do you accomplish the following conversion? Taking this alkyne and giving yourself the alkene. Well, if I look at this, here is sodium amide. What would that do? That would deprotonate this. You would not have reduction. Here is hydrogen in the Lindlar catalyst. Will that give an alkene? Yes. It will gives you syn addition, but here neither cis nor trans matters because it can't be cis or trans. Would sodium and ammonia give you reduction? Yes. You would have reduction of this to the alkene, and the hydrogens are added trans, but again, it doesn't matter here. So what would be the correct answer? D. Either B or C would work. What is the product of acid catalyzed hydration of 1-hexene? Well, we haven't really even gone over acid catalyzed hydration. It's not used very often because it can cause side reactions. But if you think back to what you learned with the alkenes, acid catalyzed hydration of the alkenes adds oxygen in Markovnikov fashion. So what would we make? We would make and enol with the ol on the internal carbon. If the ol is on the internal carbon, what's going to happen is the enol is going to rearrange and make a carbonyl. So if the oxygen is on the internal carbon, you're going to get it here, and then rearrangement to the carbonyl gives you this ketone. Both of this and this can be eliminated as possibilities because the oxygen is on the less substituted carbon. This can be eliminated because the ene is internal, and this is 1-hexyne. What product will be isolated when an excess of hydrochloric acid is added to 1-butyne? Well, butynes will add hydrohalic acid 2 times. How is it added? It's added in a Markovnikov fashion, so the chlorine would end up on an internal carbon. That means we're going to make a butane with the chlorine on the inside carbon. So it's going to end up being 2,2-dichlorobutane. Which is the following acid here? Which of the following is the strongest acid here? Sorry. Well, if I look at these, butyne is more acidic than butene. Butyne, though, is less acidic than water. And ammonia is less acidic than water. So what's the strongest acid here? Water is. So which of one of the following is the weakest acid? Well, we know water is the strongest one, so we can eliminate that. And ammonia is a weaker weaker acid than water. So let's compare ammonia now to butyne. Which is the stronger acid? Well, butyne is a stronger acid than ammonia because sodium amide will deprotonate 1-butyne, so 1-butyne must be a stronger acid. But sodium amide will not deprotonate butene. Well, that means butene must be a weaker acid than ammonia. So the weakest acid here is butene, excuse me. So write the conjugate bases of each of these and rank their basicity. Okay, if I look at water, ammonia, 1-butene and 1-butyne, the conjugate bases are made by removing just one proton. So water, it would be hydroxide. Ammonia would be the amide anion. The butene would be this anion here, which is butene with one proton removed on the end. And then 1-butyne would have its terminal proton removed also. Since water is the strongest acid, and then butyne, and then ammonia, and then 1-butene, the strongest base would be the 1-butene anion, followed by the ammonia conjugate base, which is the amide anion, then by the butyne conjugate base, shown here, and then the hydroxide. So here is the order of the bases strength. So which of the following would be the best sequence of reactions to prepare cis-3 nonene from 1-butyne? Well, if I look at 1-butyne, in order to get to 9 carbons, I would have to add 5 more carbons to the butyne. So the first thing I'd have to do is deprotonate this and use it for SN2 with an alkyl halide. So the only conditions that would deprotonate 1-butyne would be those of sodium amide and ammonia. So I can discard both C and D because of that. Both of them are followed with 1-bromopentane. Now, if I look at the reducing conditions in A and B, you would see that in A we have hydrogen and a Lindlar catalyst, and in B we have sodium and ammonia. Sodium and ammonia give us a transalkene, and the Lindlar catalyst would give us a cisalkene. So the best sequence would be to use the first one. How can you best explain the greater acidity of the terminal alkynes when compared with the alkenes? Well, if I look at this, the first one says sp hybridized carbons of the alkyne are less electronegative than the sp2 carbons of the alkene. This is not true. If anything, the electrons are held at a lower energy, and so they're being held more tightly onto the carbon, and that makes it a little bit more electronegative. The 2 pi bonds of the alkyne are better able to stabilize the negative charge by resonance. Well, this is not possible because the sp hybridized anion is held at a 90-degree angle to the pi bonds, and so the pi bonds can't do anything to either stabilize or destabilize the anion because there's no overlap at all. In C, it says the sp hybridized carbons are more electronegative than the sp2 carbons. And this is basically true. The sp hybridized carbons are held at a lower energy, and so they basically are held tighter to the carbon, and that makes them more electronegative. Answer D says the question is incorrect, that alkenes are more acidic, and that is not true at all. Alkynes are much more acidic than alkenes.